Well, hi there, boys and girls. Today we're going to take a look at the second fundamental theorem of calculus, which is really just the FTC part 2. And we're going to investigate something before we actually state it. So let's say that I want to take the derivative of an integral. Now I know that sounds crazy, but we can actually do this. We're going to be encountering functions that are defined by integrals, and we're going to want to know things like when is that function increasing or decreasing, points of inflection, and the only way you can do that is to take the derivative of that function. So yes, we are going to take derivatives of integrals, and we need to be able to do this with relative ease. So let's do this, what I would consider, I guess, the long way. We're going to work inside out. I don't know why that switched to black there, but there, it's purple now, so that's better. I'm going to integrate t squared from 1 to x, and then we'll take the derivative of that. So let's see what that would look like. So I would take the derivative of the integral of t cubed, or the antiderivative of t squared, is t cubed over 3. And we would evaluate that between our bounds of 1 to x. So I'm working inside out. I'll do the derivative at the very end. Our next step here would be replace t with x, so that's going to be x cubed over 3, and then replace t with 1 and subtract those values. That's what the fundamental theorem of calculus part 1 told us to do. So I have inside here, I have my answer to the integral. I have done the integral. Notice that the t is gone. It's no longer a t because I replaced it with an x. That's what the FTC told me to do. Alright, so at the very end here, I'm going to take a derivative. So the derivative of x cubed over 3 just works out to be x squared. And the derivative of 1/3, well, that's 0. So I'm not going to write minus 0. I'm just going to say my answer is x squared. Let's try another one. We're going to work inside out. So I'm going to do the integral first, and then I'll take the derivative at the very end. So I'm going to do the derivative of the integral of cosine, or the antiderivative of cosine, is sine. And I'm going to evaluate this between pi over 6 and x. Alright, now my fundamental theorem of calculus says you plug the top number in first, replace t with x, so that becomes sine of x, and then we're going to replace t with pi over 6, and we're going to subtract that. And the sine of pi over 6, of course, is 1/2. Alright, so I've done the integral, I've worked inside out, so now I'm going to take the derivative of my answer. And the derivative of sine of x is cosine x, and the derivative of 1/2 is, well, it's 0. And I don't care what that number was, that's going to be, I don't even care if it's 50 or a billion, that's always going to go away. So my answer here is cosine x. Now something pretty neat happened here. This is showing me that derivatives and integrals basically are inverse functions of each other. They will undo what the other one has done. It's just some minor things are going to happen. If you take the derivative of an integral from a to x, where a is any number, I don't care what if a is negative, I don't care if a is 0, I don't care if a is 50 billion. At the end, it's going to go away because of the derivative. So if you take the derivative of an integral, the derivative and the integral basically cancel each other. The only thing that you have to pay attention to is that the t will be replaced with x. And I showed you why that happened up here, because the FTC told me to do that. So this is a shortcut that we need to embrace. The derivative of an integral basically cancel. The only thing is you plug your x in for t and you're done. You do not need to do it the long way. If you don't learn this today, fine, do it the long way, but that would be really silly. Just replace the x for your t. Now what if I have a x on the bottom and I'm going up to a number? Well, we should know that we have the right to flip this around. I could do negative derivative of our integral from 4 to x. You have the right to switch these if you want. Just make sure that you negate your integral if you do so. And then I've got t squared here. So I've turned it into the fundamental theorem of calculus, so my answer is, keep the negative there, the derivative and the integral basically cancel each other. I don't care what this number is at all. Yeah, you could be a 4, you could be a 40 billion. Doesn't matter to me. All that's going to happen is this x is going to be replaced for your t, and I'm going to get negative x squared. The derivative and the integral basically cancel each other. The x goes in for t, and that's your answer. So if the x is not on the bottom, I'm sorry, if not on the top, it's on the bottom, you're going to say this is negative f of x. All right, so let's take a look at the chain rule version of this. I guess we could do this the long way, but okay, fine. We'll do it the long way so you'll see, because this is very important for you to see. So we're going to do this the long way. So we're going to work inside out. The first thing I'm going to do is do the integral of cosine of t, and then I'll take the derivative. So let's do this. The antiderivative of cosine of t, of course, is sine of t. And we're going to evaluate this from pi over 6 up to x squared. Alright, so the fundamental theorem of calculus tells me to plug the top number in first, fine, sine of x squared. And then plug the bottom number in, pi over 6, the sine of pi over 6 is 1/2. So I've done the inside part. Now we're going to take the derivative. The derivative of sine of x squared is cosine of x squared. I think you know what's coming here because you even see chain rule down here, times 2x. And the derivative of 1/2 is just 0. It goes away. So what had happened was you had to put the x squared in for t, but if this upper limit is some function of x, some other function of x, you must multiply times the derivative of that upper limit. Again, the lower limit does not matter at all because we take the derivative of the number, it goes away to 0. This does not matter as long as it's a number. So the second fundamental theorem of calculus chain rule version looks like this. The derivative of an integral from a number up to a function of x, of f of t dt, will be f of g of x. The first thing you do is plug in g of x for all of your t's, then multiply that times the derivative of g. Let's take a look at a couple examples here. Second fundamental theorem of calculus to evaluate this, the derivative and the integral are going to basically cancel each other. I'm going from a number up to x, and all I'm going to do is replace the x for the t. This is really easy once you learn this shortcut. So we replace the x for the t, and we get the square root of 1 plus x squared. Now I could multiply this now times the derivative of this upper limit, but the derivative of x is just 1, and I'm not going to write that down. So part B, the derivative and the integral basically cancel each other. We're going from 2 to x. I don't care if this is 2 or 3 or 5 as long as there's a number on the bottom. The x gets plugged in for t, so this becomes tangent of x cubed. And again, I don't have to multiply times 1. Now here's an example where the upper limit is not just x, it's a function of x. So I've got to use the chain rule here. So my derivative and my integral cancel each other. I'm going to replace the t with x cubed, not just with x, with this whole function x cubed. So this becomes 1 plus x cubed. And then we're going to multiply this times the derivative of the upper limit, times 3x squared, which we could write if we wanted to as 3x squared over 1 plus x cubed. Now, did the negative 1 matter? No, it does not matter because when you take the derivative of a number, a constant, it's just 0. Here I've got a number up to a function of x, so the first step is the derivative and the integral are going to cancel each other. The sine of x is going to be replaced for all of your t, so this is going to become the cube root of 1 plus sine of x squared is sine squared of x. And I'm not done. I have to use the chain rule. I have to multiply this times the derivative of the upper limit. And of course the derivative of sine is cosine. Once you learn this shortcut, it should be super duper easy. So let's take a look at an example of a free response question. This is a very common free response question on the AP Calculus exam. I've got a graph of f. This is f, this is f, this is f. Now make sure my brain knows that this is f. And they're going to define g as a function of f, and we're going to be the integral from 0 to x of f of t dt. So we have a function defined as an integral. That's fine. Let's find some values for g. G of 0 is going to equal, you just replace your x with 0. It's going to be the integral from from 0 to 0 of f of t dt. And we know that if the integral's limits match, we have no width, and so we have no area. All right, g of negative 1 is going to be, replace your x with negative 1, we get the integral from 0 to negative 1 of f of t dt. And we know how to deal with that. Negative 1 is actually smaller than 0, so we want to flip this around. And we're going to call this negative integral from negative 1 to 0 of f of t dt. And we've just spent a long time understanding what an integral will do. An integral is the net signed area under the curve of the graph between your values negative 1 and 0. So let's go up here and look. Negative 1 to 0, this makes a nice little triangle. Has a height of 2 and a base of 1. Or you can maybe just count boxes. But the area of that triangle is 2 times 1 divided by 2, so this area is just 1. And it's above the x-axis, so I can call it a positive 1. So the integral from negative 1 to 0 is 1, but looky there, there's a negative out here waiting on us, so that answer is negative 1. Let's find g of 2. G of 2 is the integral from 0, we're replacing the x with 2, 0 to 2 of f of t dt. And we know how to interpret that. That's the net signed area between 0 and 2. Well, here's 0 and here's 2. This area under the curve, that's a quarter circle. That circle has a radius of 2, and so the area of a full circle with a radius of 2 is pi r squared, so pi times 2 squared is 4 pi, but this is 1/4 of a quarter circle, so this area here is just pi. So we're going from 0 to 2, that area is pi. Now what about g of 5? G of 5 is going to be the integral from 0 to 5 of f of t dt. So let's go see about that. We've already gone from 0 to 2, so I know it's at least pi. Now what happens after 2, from 2 to 5, is f drops below the x-axis. And so when we find this area here of this weird little shape, we must call it a negative area. So I'm going to subtract off from pi all of this area. And I think it'd be pretty easy just to count boxes here. 1, 2, this is a little triangle here that has an area of 1, and this is a triangle that also has an area of 1. So 1, 2, 3, 4. This has an area of 4, but we have to subtract it off because it's underneath the x-axis. The graph is underneath the x-axis, so the integral is going to be a negative value down there. And pi minus 4 is going to be less than 0. I'm going to need to know that in a little bit. Pi is 3.14159, blah, blah, blah. We subtract 4, we're going to get a negative value, but we're not going to quite get back to negative 1. So let's stop for just a second and understand what happened. G is an integral of f, so g actually increased from negative 1 to 2, and it increased a value of pi plus 1. Then g decreases because its derivative is below the x-axis, so g decreases by a value of 4. So we start at negative 1, we go up 1, we go up pi, so we've gone up about 4.14, then we drop 4, so we're dropped down to about 0.14. That's going to be very important for a question I have down here in part D. Alright, so part B, find all values of x on the open interval at which g has a relative maximum. This means I need g prime to go from positive to negative. I need g's derivative to cross the x-axis. Well, what is g's derivative? G prime of x is going to equal the derivative of the function defined by g, which is right up here. So I need the derivative of the integral from 0 to x of f of t dt. So this is why we need the second fundamental theorem of calculus. We're going to need to be able to take the derivative of an integral. The derivative and the integral basically cancel each other. The only thing that happens is x comes in for t, and we get f of x. So this graph right here is the derivative of g. G prime is equal to f. So when does any function have a relative maximum? It has a relative maximum when its derivative goes from positive to negative. So here is a picture of g prime. G prime, which happens to equal f, crosses the x-axis from positive to negative, which is what we need. That's our definition of a maximum, at least a relative maximum, crosses the x-axis in a specific way from positive to negative at x equals 2. So I've got my answer and my justification. All right, find the absolute minimum value of g on -1 of 5 and the value at which it occurs. Justify your answer. Absolute minimum can also occur at endpoints. So I've got to use my candidates test. And I'm going to list x values here, and I'm going to list g's value at all critical points and all endpoints. Even though I know for sure that the only critical point that g happens to be a relative maximum, but I'm still going to include it. My endpoint of -1, the only time that g's derivative crosses the x-axis at all, either from above to below or below to above, happens right here at 2. This is the only critical point on this graph. It happens to be a relative maximum, so it's not even a candidate for an absolute minimum, but I'm still going to include it. And then also I've got an endpoint of 5. And I really like now that we did the work in A, because we answered this. G of -1 worked out to be -1 from A. G of 2 worked out to be pi, and G of 5 worked out to be pi minus 4. And you just want to look and see the smallest value you see here, -1, pi, and pi minus 4. That is the smallest value. Pi minus 4 is negative, but it's not quite to -1. So the absolute minimum of g is -1. And it happens at x equals -1. That's sort of nifty. And my justification is right here, my candidates test, but I need to say something. I need to say that after -1, g prime, which is equal to f, I need to actually say equals f, g prime equals f, was above the x-axis more than it was below the x-axis. So I'm not going to write all that out, but I can say from my previous statements that g increased more than it decreased. That's how I was arguing up there at the in A. G increased more than it decreased. All right, find the x-coordinate of each point of inflection of the graph of g on -1 of 5. So I need to talk about g double prime changing sign. Or we can also do this whenever g prime changes direction. Having a hard time with my air slate here. Sorry about that. I'm glad you can hear me, because you definitely can't see that says changes. So that would occur at 0. Does it change direction right here? No, it doesn't change direction. It's got sort of a sharp turn, and it also changes direction here. So we need g double prime, which is f prime. We need it to change signs. So we've got positive slopes, then we've got negative slopes. So this is going to be a point of inflection. We have negative slopes, and then we have positive slopes. So g double prime, or f prime, changes sign at 0 and at 1, 2, 3. And I'm going to argue that it changes direction. So I'm going to say that g prime, which equals f, changes from increasing to decreasing at x equals 0, and then also it changes, not it, f, which is g prime, got to appeal to a change in a derivative, changes from decreasing to increasing at x equals 3. I know that was a lot, but this is almost a guaranteed question on the free response part of your AP exam. I will see you guys tomorrow.